So I am going to be talking about some of the theories, ideas, and concepts behind the enhanced sampling methods that we use, especially not so much the kinetic stuff. Sapna will talk more about enhanced sampling for kinetics, but I'm going to try to provide an overview of a lot of the different enhanced sampling techniques there are. So, and really dig into the concept. So why enhanced sampling, right? Like we talk about, this is the workshop on enhanced sampling. Why do we need it? And basically, it's because of something called the multiple timescale problem that happens all the time in almost all molecular simulations. Whenever wiggling of atoms is involved, you're probably going to have a multiple timescale problem. So interesting molecular processes involve multiple timescales that are very, very different. If they just involved slow motions, we could come up with algorithms that just did very large jumps in time, but they involve things that are both very, very fast and very, very slow. Here, biological is what I know the best, but we'll talk about some similar things in others as well. Bond vibrations are down around 10 to the minus 15 seconds or so, but things like solvent rearrangement may be 1,000 times longer. If you're dealing with proteins, the side chain rearrangements, those are relatively fast, maybe a nanosecond, maybe. But loop rearrangements, when things start folding up and down, those are longer. Binding and unbinding of ligands, or even binding and unbinding of proteins together, is another 1,000 times slower than that. Cellular transport, we're getting into the seconds, and life is, on the 10 to the 3, 10 to the 6 time scale. So it's really hard to come up with an algorithm that can both capture the local motion and capture the long timescale motion. So most molecular dynamics techniques, in order to actually get the physics right of the small molecular vibrations or rearrangements, need to take very small time steps, need to advance in time a very small amount. And that means they can't really access the timescales needed to get to other important events. If you're dealing with, catalysis on a surface, then again, the bond vibrations take the same amount of time. But a lot of times the rearrangement, once a molecule is bound to the surface, the rearrangement it might need to take to get from the initial binding pose to the actually catalytically active pose, that could be nanoseconds or longer. And then actually jiggling around till its internal vibrations are in exactly the right position that it reaches the transition state. Again, that might take milliseconds or so. And so all of these aspects, it's a multiple timescale problem. If you're dealing with, say, polymers, and you're looking at you've got, if you're looking at cross-linking of polymers, you've got a time scale of the reaction, but then that might be, the actual reaction might happen quickly, but then you have to have the reorientation time for the polymer to move around and actually get the next reactive group present. So all of these have multiple timescale problems. Whenever there's molecules, there's multiple timescale problems. So enhanced sampling, if you're interested in thermodynamics, if you're trying to find things like binding for energies or average energies or configuration ensembles, anything to do with the thermodynamics of statistical mechanics, the basic concept is break some physics laws, but not others. Specifically, what do we want to keep? The Boltzmann distribution. This is the main thing. We know if we got the Boltzmann distribution, then all the thermodynamics will be there. And what we can break, any sort of continuity of molecular trajectories. We don't care how molecules get from one place to the next, as long as, we'll talk about that later when we do care about how they get from one place to the next. But for the first few days, we'll be looking at cases where we don't need to worry about the continuity of the molecular trajectories. We just care about that they're there where they're supposed to be the right amount of time. F equals ma. We don't need that. We don't need F equals ma because all we care about is rules that do satisfy the Boltzmann distribution. So we can break F equals ma. Any sort of kinetics we don't care about. We can break those laws and come up with algorithms that just obey sort of the laws that we care about. So that's generally the principle. Or if you, and then when you break the laws, sometimes you will need to figure out how to correct it. So you have to be able to correct it in a logical way. I'm going to pause there for a second to see if there's any comments and questions. So, yeah, I won't get there. Okay, I'm going to keep going for now because I'm still sort of in the middle of this introductory part. So enhanced sampling for kinetics, Kinetics are a lot harder than thermodynamics because you need to not just know about how molecules are distributed, what their probabilities of the different configurations are. Trajectories are a series of configurations. So anything dealing with a series of configurations is going to be more complicated than just dealing with individual configurations. There, you're going to break a lot of these things, whether a trajectory is fully continuous or not, but you're going to have to break it in ways that one can recover the results afterwards. And Satna will talk a lot more about this at the end of the week. How can you stitch things back together? Part of it is discretizing the trajectories a little bit, and we'll talk about when you can do and when you can't do that as well. So you tear it all apart, but tear it all apart in a way that you can put it back together afterwards. So before we go, what we're going to do, if we're going to play fast and loose with the rules, we have to be very careful that we know what rules we have to follow and which rules we don't. What are the general principles we can use? If we can't rely on just nature to do things. We have to think, what are the rules? How do they work? And how are we going to be able to break them? So I'm going to do a complete overview of using simulations to calculate thermodynamics in 5 minutes. It'll probably be a little bit more than 5 minutes, especially if it's in questions. But I want to get at the point that there's actually a relatively few number of things that we need to get exactly right. Once we bring in all the molecular details, you got to think a lot more about this. But the basic ideas, they're not necessarily easy, but they're a small number. So first, the concept that all thermodynamic properties are ratios of highly multidimensional integrals over the coordinates. So what am I talking about here? So here I've got integrals over the Boltzmann factor, and I've sort of encapsulated the temperature and the energy all together. Boltzmann distribution, you've got E to the minus this reduced potential energy. So when you integrate that, you get the free energy of one state. And if you're interested in the free energy difference, you're just looking at the ratio of these two integrals, the Boltzmann distribution at one state over the Boltzmann distribution at the other. They could be different by temperature, they could be different by the pressure, they could be different by your force field you're using. But if you want a free energy difference, you're going to calculate the ratio of these two integrals. Okay. And then if you're interested in some ensemble average, and by I mean any observable for the system. It could be the volume of the system, the radius of gyration of a polymer in that system, the fraction of whether a particular configuration is reaction capable or not, and maybe you're looking at some probability of that. So for all of these things, these are weighted averages. And so to calculate a weighted average, we multiply every single observation by the Boltzmann distribution. But then we have to normalize that by the sum total of all the configurations, right? This is the same factor here. We weight the observable, but then when we weight it, we need to divide by the Boltzmann factor to have this be a well-defined average. So it's just a weighted average over all the configurations, and the weight is the probability distribution. Any questions on this? I'm going to wait it because this is important to get this concept down. You've probably seen it before, but just want to check. I don't know if people are there's no people posting in QA. No questions for this. Okay, please do not. If we're going a little faster and you need to post the question after, that's fine. Okay, so that's the first idea. But multidimensional integrals are hard. I don't know. I remember back in like taking multivariate calculus, trying to do integrals over like X, Y, and Z, and that was excruciatingly painful. Remember, if you're dealing with molecules, then the number of coordinates you have to integrate over is the number of atoms times 3. So 10,000 atoms, 30,000 degrees. You cannot do an analytical integral over 30,000 dimensions. So what we do in molecular simulations is we perform Monte Carlo integration of these ratios of integrals. So what do I mean? So this is a normal weighted average. We have a probability times an observation, and that gives us an average. And so what we do is we replace that, and this is the key trick here. We're replacing this integral by an average But here's the key, is that x and n are sampled from our probability distribution. So if we can pick x's from our p of I, once we pick all of those, then if we simply take the observation at those points we sampled from and do it plain old normal average, just add them all together, divide by the number of samples, these will converge. And this is not quite an equal. What this is if you do this for enough times, you'll get this answer. Yeah, this is equal to the value of the integral plus a little bit of noise. So that is the key, is we replace a multi-dimensional integral with like 30,000, 100,000 things we need to integrate over with sampling from a distribution and then just averaging things together. That's the key. And this is, you might have wondered, we're supposed to be calculating things with the Boltzmann average. If you run a simulation and calculate an average energy, you don't use the Boltzmann factors. You don't try to weight the average, even though it's the Boltzmann distribution. The Boltzmann factors are already there when you run the simulation. The simulation is generating the Boltzmann factors. So all you have to do to calculate quantities is average over what you see. So that is the key behind really all these methods. And this is important to remember. So we then generate these samples using, for example, one form of Markov chain Monte Carlo. Given the current state, assuming it has the right distribution, select a new state that preserves this probability distribution. And we'll talk a little more about this going for a little bit later, but many of you have used Markov chain Monte Carlo. And eventually, there's a little asterisk there, because eventually might be a very long time indeed. If you use this algorithm, it will sample from the right distribution. Molecular dynamics is another way that many people have used here for this. It's actually, you can actually think of it as a type of Markov chain Monte Carlo. Your step, your new place you're going to, is in the direction of the force with 100% acceptance. I put an asterisk there because actually, if you're being super, super, super rigorous, then it's like 99.999% acceptance, and you can slightly improve the statistics if you eliminate some noise if you actually put a Monte Carlo accept and reject. But in most cases, you can forget that. You get close enough by just accepting every single move you make with molecular dynamics. In molecular dynamics, all we're doing is applying Newton's equation of motion to generate new. Oops, there's a square missing there. I'll fix that afterwards. So it's you're solving the coupled PDE by initial value problem, if you want to think about doing physics in the applied math context. So that's what many people who are on this call do already. So whatever the method, here's the key: it's going to have very long correlation times, meaning you might start you're sampling all your local behavior, but it might take you a very long time to get to another configuration that's of interest, like a protein unfolding or a polymer relaxing, because it's a multi-scale, time-scale process. So so either you have to be able to run your simulation for long enough, which could be 100 nanoseconds, which is doable but annoying, or it could be multiple seconds, in which case you can't do it with molecular dynamics unless you have some way of breaking these long correlation times. So that's the last part. So that's all pretty easy. People knew all about this in the 50s and 60s. From there, we need to identify improved ways to accelerate sampling through the multidimensional space of interest if we can't do it directly. And there's a lot of things that people have come up with: umbrella sampling, replica exchange, Hamiltonian replica exchange, accelerated MD. That's a really bad name, by the way, but that's a specific method because lots of ways to accelerate MD. Multi-canonical simulation, adaptive biasing force, weighted ensemble, metadynamics, on and on and on. It is a zoo. There are new methods published every week, I would say. And I do want to put an asterisk there because I would say most new methods, half the time, they're rediscoveries of old methods or special cases of old methods. So there's a lot out there. Another useful thing is to identify improved ways to estimate multidimensional integrals, giving a set of molecular simulation data. The easiest way to do this is to just use the formula we saw for Markov Monte Carlo integration. Average all the observations you make. But there's a lot of ways to get a lot more information out as well. Free energy perturbation, there's a lot of these as well. So that's it. That's the complete overview of what people are doing. You want to sample from a probability distribution, you want to get information from it, you want to calculate these integrals, you run the simulation, collect the data, and then figure out ways to sample from pi of x better and extract more information out of those. So I do actually want to take some comments. I will not go on until there's a question or two, because that's everything, right? That's all. That's everything there is. We just need to get into the details from here. Clearly, that is not, it does not explain everything. So I would love to have some questions in chat. I don't know if people are raising their hands. I can't see that. Just
Yet,
put them in chat.
Folks, you can put it chat. You can raise your hand and just ask a question also.
Can you use parallel tempering with free energy calculations? We'll get to that later. Yes, the details we'll cover later. Is there any important classification for this method? That's a really great question. No one has come up with a complete classification. Myself and a few other people have tried to do this. I did not actually put a link to that paper in these slides. I'll definitely do that on Friday when we sum everything up, but I'll put it in chat afterwards. There's ways you can classify this, and I'll talk a little bit about that in a second. But I'll send up when I'm not talking. I'll put a link to that in chat later. How do we know which method is the most appropriate for our systems? We're probably not going to be able to get into that more directly in the lectures. It'll come up from time to time, and maybe when we talk about specific methods, we can talk about specific things. It gets complicated because most methods work with most systems, but some are more appropriate than others. So we can talk about some of the features and get a little more on the more appropriate ones. That is the question, and we'll try to talk about that in some specific cases. Which system scale do you use these missions? What system scale? So that's what system scale? That's a really great question, and I think it does depend on the methods. Some methods are better for larger systems. Some are better from smaller. A general modeling thing is use the smallest system you can get away with to answer your question. That's always a good thing. Sapna found the i-CoMSE paper where we actually do have like a diagram trying to classify all the methods and talk about the ingredients. So the system scale, we'll talk about system scale when we can, and we'll talk about when some methods perform poorly at different scales. Okay, how do we know the method works efficiently? That is something we will talk about when we talk both of the methods. How do we know that they're actually working to do what they're intended to do? So that will be discussed as we talk about each method each time. Great, so those are great questions. Okay, so let's move forward a little bit now. Do each of these methods largest source of error? So what's the largest source of error? Assuming you're implementing, these are good questions, so I'll keep answering. Largest source of error when using these techniques. The largest source of error is still lack of sampling. Whenever you use these methods, you usually overcome some sampling barrier, but not necessarily all of them. So usually the biggest problem is there's something you didn't take into account in that. The second largest source of error is misuse of the method. So this is one thing hopefully this workshop will help to address more. Do each of these methods agree with each other? Is it possible for there to be discrepancies in the free energy profiles depending on the problem? I would say if implemented correctly, the methods we're going to talk about, and most others, unless they explicitly say there's an approximation, when you run them long enough, when you discretize things closely enough, they should agree because they're all designed to be consistent with the underlying physics. So one thing I like to do, like for free energy calculations, when I wrote up like my scripts for this, I wrote up like, I usually had like 5 different ways to compute the free energy and made sure they agree with each other. Now I'm not so paranoid. I just like check to make sure that 2 ways agree. So that's a good way to know if you're doing something wrong, if different methods disagree. Are any of these applicable? We know very little about the energy landscape beforehand. So one thing I would say is almost always when you're doing molecular simulation, you don't know nearly as much about the energy landscape as you think you do. And so we'll probably talk more sort of in wrap up about ways to do that. We'll mention that throughout. Yeah, so that's a great thing to keep in mind as we go through to include talking about that as well. The more you know about the energy landscape, the more you can tailor your methods towards it, though. Okay, cool. So this I like to talk about this Taco Bell formulation of enhanced sampling. So what do I mean by that? So if you go into Taco Bell, if you actually look at what they got there behind the counter, there's not that many things they have. You know, you got some tomatoes, some guac, some more or less ground beef, some sour cream. You know, there's a few things. That's pretty much all they got. But as you may know, Taco Bell doesn't have quite as many ads as they used to, but they are coming up with new menu items like every few months for the last 20 years. And the reason is combinatorics, because there's all sorts of different ways you can put things together. What's on the inside? What's on the outside? What do you first? What do you put on one layer? What do you put on the next layer? And that's a lot about what enhanced sampling methods are. There's only a limited number of ingredients. And if you understand what the different methods are trying to do, then you can figure out, you know, how good those are. Constructing biases along a collective variable, we'll talk about that. Introducing dynamics along an auxiliary variable, expressing as a maximum likelihood problem. That's very common. Using importance sampling to calculate unsampled averages. We'll talk about that. Accumulate partition function adaptively. Yes, that'll be something that comes up a lot as well. Machine learning is a new thing to put in quotation marks, because there's a lot of things you can do with that. So we're going to talk about, we're not going to be able to cover everything. We've got a 60-page paper that Sapna did a link for that tried to do everything, and we still didn't quite make it. But we're going to talk about the main ingredients here that go into the methods, and you'll see they come up again and again. So that's the formulation. There are a lot of things. Once you learn the ingredients, you can see how they all combined. Okay, let's understand the Boltzmann distribution a little bit more. Let's dig into this. And I think there's one subtlety that's missed sometimes that I want to address. Okay, so one important thing, it's often much clearer to work with the probability than with the energies. A lot of methods that look really confusing, if you back up and say, let's not look at it in terms of the energies, let's look at it in terms of the probability distributions, things simplify a lot. They're not completely easy, but they're simpler. So here, for example, here we got the Boltzmann distribution. The probability of some configuration, and I have an I here because, you know, could have different potential energies, is proportional to e to the minus beta, where beta is 1 over kBt. So the higher the temperature is, the flatter this distribution is, the more even it is. Beta times u of I of the energy of that configuration. Now this is super important, right? This symbol means proportional to. So what's the constant of proportionality? Well, if you remember, the constant of proportionality, if you remember, is if you think about probabilities, if you add up all the probabilities and sum them, that has to sum to 1. And if it doesn't sum to 1, you add up all the probabilities and divide by that number, well, then it will be 1 by definition, because you're dividing by the sum of everything. So here, the partition function, if you remember, is the sum, or the integral, if it's a continuous space, of all the Boltzmann probabilities. So that is, oh, probably you don't need, okay, yes, I need to be over here. I'm looking at the wrong one. Waving my mouse on the wrong one. Now you can see the mouse, right? Yes, okay, so it's the sum of all of these. So that is the normalizing constant, the partition function. We call it a normalizing constant because when you divide all these unnormalized probabilities together by this, then they all do sum up to 1 like they're supposed to, like a real probability distribution. So this is another way to express the normalized probability distribution. It's e to the beta a, where a is the free energy. I'm using a because it could be Helmholtz, or well, a is common for Helmholtz. It could be any free energy, Helmholtz or Gibbs, depending on what, you know, whether you've got pressure or not. But generally, for all these ensembles, you'll have e to the beta free energy minus beta ui, and this is a normalized probability distribution. So this is not really a probability distribution. It's this that's the probability distribution. So whenever you see that, you go, aha, that's a normalized probability distribution. I can start sticking that in statistics formulas. Okay, so let's say we need to do some sampling. Our goal is to sample representative xi from all the distribution. The problem is the distribution looks like this. You've got, if there's 10,000 atoms, means it's a 30,000 dimensional problem. There's the actual occupied configurations are just the, imagine it's a really poor water year. So you got a really low water level, a very narrow area that there's actually water. That's the configurations we care about. The rest of these are high energy configurations we don't care about. Only a vanishingly small fraction of the xi have high probability or low energy. So this is the toy problem we're going to play with for a while. It's super, super simple, right? We got two minima. 1D is way easier than multiple dimensions, but the advantage is we can actually visualize things a lot more. And yeah, and we know the surface, right? We can look at it and we say, well, that's the potential energy surface. We can, and so it's going to be a good way to play around with things. So let's go to the notebook. We've got 5 minutes. I think we've got enough to get going. So let me share, stop share, new share. We might go a couple minutes past, but just to get a good part. So let's go here. So here I've got the, I've clicked on demand. I've clicked on the Jupyter Notebook point, and I'm going to go for, I guess we can't do fractional hours. I'm going to go for 2 hours just to be safe. One node. Make sure you pick RM shared so you're not taking a huge amount of nodes. Very important to get this right. Partition, RM share. Extracellular marks. I think this is safe for my previous one, but minus n task per node equals 1. We just want 1 core, and we don't need any extra arguments. So minus n tasks per core, 1, just one node, and definitely RM shared. And now I can just launch this. And it will, might take a second, because probably everyone else is doing this at the same time. Or is it opening it somewhere else? Is it opening it somewhere else? Oh no, it's thinking, it's thinking. There we go. Probably, it usually happens almost instantaneously, but probably everyone is doing it at this time, so it's slightly slow. Didn't expect it to take this long. There we go. Okay. So I'm going to connect to Jupyter. And it's a thinking. And I'm going to go to the advanced sampling workshop. I'm going to go to Monday. And I'm going to go to toy model for sampling. And one thing you'll want to do to make sure you have the right environment, I'll do this when we it loads. Okay. So now we'll get this up and running and get the toy model sketched out, and then we'll take a break before we get into the sampling. Okay, so what you want to do is go to kernel. So notice this is with Python 3 kernel. We want to change the kernel to i-CoMSE CPU. So just kernel, change kernel, i-CoMSE CPU. It'll restart. There we go. Now we're set. And so that'll make sure we have the right. Oh, yeah. Try restarting out. Yes. Okay, now it should be with the right kernel. Great. There we go. Now it's got the right kernel. So we'll do some imports. Most of these are standard ones. PyMBar will come along with this. Ignore that warning. We need to not have that warning happen as much. And I'm going to define my potential here. You can play around this later and alter them later. So we define locations of our minima. And we got cutoff regions here where we transition between one minima and the next. Value at the bottom of the first minima, slightly lower at the second minima. I'm defining a bearer, height, spring constants. And so this function is the lower minima, right? It's harmonic, x minus the mean squared. Here's another harmonic one for the upper one. And then just using a Lagrange interpolation formula to smoothly connect the two in between. And that's my potential. Here I'm using the NumPy piecewise function to say, okay, below the cutoff, it's the lower one. Above the cutoff, it's the upper one. In between, it's this interpolated potential. Let's plot it. Great. All right, that looks nice. We've talked about the probability, how important the probability distribution is. I was emphasizing, you don't want to look at just the energies. You want to look at the probability distribution. So what does the probability distribution look like at different temperatures? Since we're interested in ensemble average properties, let's also look at the average energy as a function of temperature for the system. So let's run this code. So what I'm doing here, I'm looping over the temperatures. And here, now integrating in 3 dimensions or 30,000 dimensions is really hard, but integrating over 1 dimension is pretty trivial. So we can actually calculate our partition function here. And we can calculate our free energy. We just minus temperature. We're assuming KBT. We're doing this in units of KBT, so we don't need to multiply by KBT. Here's our free energy. And our energies are, we integrate the function of multiplying the potential by the Boltzmann weight divided by this partition function. And so then we can plot the probability, where the probability is the Boltzmann distribution divided by our partition function as T. And so we see at low temperature, the second harmonic well was about minus is 2. So the second one is a little bit lower. So at low temperatures, we're much more likely to be in the second minima. At 1, they sort of even out a little bit more. At 5, more so. And at 20, it's pretty much, it's hovering around the minima, but it's actually sampling some of these intermediate locations as well. So looking at this, that tells us sort of what's going on at a bare level. But we look at probability of visiting things, we see something different. And it's this that you want to be thinking about most of the time when you're thinking about sampling. With a 1D potential, it's pretty easy to go back and forth, but it's harder with other ones. Let's look at the average energies. So the average energy at low temperature, it's mostly here in this well that has a minimum of -2, so -1.7 makes a lot of sense. And then at the higher energies, this average gets a little higher because we're both getting contributions from both wells, and also it's spreading out a little more. It's occupying more of this harmonic basin. And then at higher energies, then you get, you start going further up the well, and so your energies go up more. And we can look at the free energy as well. It's a little harder to interpret exactly what that is in absolute terms, but it gives us a sense of what's going on. Okay, so let's take a break. So what we're going to do is start sampling on the surface, and we're going to observe our multiple time step problem when we do. But we're about 3 after. Let's, since I'm the one that's after the break, I can cut into my own time. Let's start up exactly 13 minutes after the hour, and I'll stay on and can answer some questions. But if you need to head to the restroom, whatever, go take a break, and we'll see you all back here. We'll answer, we'll answer questions and stuff, and we'll see you back here at 13 after the hour.